Hello, and in this talk I'd like to run through an example of using complex impedance to solve a real circuit with real sinusoidally varying voltages and currents. This is the circuit we're going to be looking at. It has a voltage source which has a phase angle of minus 90 degrees and an amplitude of 1 volt. So I could write that as Vt equals cosine of omega t minus pi over 2, if I'm working in radians. And I have a current source of 2 milliamps with a phase angle of 45 degrees. So I would be writing that as the current is equal to 2 milliamps times cosine of omega t plus pi over 4, which is 45 degrees in radians. Right, this theory we worked out before of using cissoids and complex impedance requires all of the sources to be cissoids. And we can achieve that if we decompose the voltage source, the real voltage source, into two cissoids, and the real current source into two cissoids. That effectively makes the circuit look like this. I have a voltage source here in series with another voltage source, so both of these add up to give you the total voltage here, the inductor there, and we'll have a current source here in parallel with another current source. So the effect of both of those current sources would add up to give you that current source. Now, I can express both of these sources in terms of cissoids by using the formula that cosine of x equals e to the power of jx plus e to the power of minus jx over 2. This means that the voltage source becomes effectively e to the power of j omega t minus pi over 2 over 2. And this one would become e to the power of minus j omega t minus pi over 2 all over 2. And I can do something very similar with the currents. This current would end up being 2 milli times e to the power of j omega t plus pi over 4 all over 2. And this current source would be 2 milliamps times e to the power of minus j omega t plus pi over 4 all over 2. I've now got 4 cissoidal sources in my circuit. So all I have to do is work out the contribution of each of these cissoidal sources to the voltage across the current source, and then add them up. Superposition should work because this is a linear circuit. Now, let's consider the effect of this voltage source first. If we just consider this source and turn it on and switch all of the other sources off, then you'll notice that no current is flowing around this circuit at all. There's nowhere that current can flow, because if both of these current sources have been set to 0, then there is no current flowing down through either of them, and therefore no current flowing through the inductor. If there's no current flowing through the inductor, then there's no voltage drop across the inductor, which means that the contribution to the voltage across the current source would just be equal to the value of this voltage source. And the same argument applies to the other voltage source as well. So we could immediately say that the contribution of the two voltage sources to the voltage across the current source, the one that would be measured by the voltmeter, is just equal to the voltage source itself. So my first contribution is just cosine omega t minus pi over 2. That's the contribution of both of these cissoidal voltage sources. For the current sources, things are a little harder. We'll consider this one first. If we only have one current source, then our circuit effectively looks like this. Current source, an inductor. That's a terrible inductor. Better. Going round That really is a shockingly bad inductor. Sorry, it's an inductor. I have a current going round that inductor, which will therefore produce a voltage across that inductor. And the voltage across the inductor, call it V1 for now, is going to be the current through the inductor times the complex impedance of the inductor. Well, the current through the inductor, expressed as this sinusoid here, is 2 milli divided by 2, so that's just 1 milli, times e to the power of j omega t plus pi over 4. And the complex impedance of the inductor is j omega L. So that's my first contribution to the voltage as measured by the voltmeter. The contribution of the other current source is going to be the other current, which as a sinusoid is 1 milli, times e to the minus j omega t plus pi over 4, times the complex impedance of the inductor. And here we have to be a little careful, because we're no longer operating at frequency omega. As time increases, the phase of this term here gets more negative. It goes down. If we think about these on an Argand diagram, this phasor here would start at time t equals 0, at that point there, 45 degrees, and as time increases, the phase will increase. This will start moving round in this direction in an anti-clockwise way. This one, however, will start at a phase of minus 45 degrees, because when t equals 0, that would be e to the minus j pi over 4. It will start there. And as time increases, the phase becomes more negative. It goes down. This sinusoidal oscillation is doing this. It's going this way, in the opposite direction. It has an effective frequency of minus omega. So if I consider what the complex impedance of the inductor is going to be at minus omega, the answer is minus j omega L, or j times minus omega times L, if you prefer. So those are my two contributions to the voltage from the two current sources. The total contribution will be the sum of these two. And that is 1 milli times omega times L times e to the power of j omega t plus pi over 4. I'll take the j outside the bracket as well, minus e to the power of minus j omega t plus pi over 4. Now, this is in the form e to the power of jx minus e to the power of minus jx. And that is equal to 2 sine x times j. Using that result, I can express the contribution of the current source to the voltage as 2 milli times omega times L times j, that's this j, plus another j from this j is j squared, times 2 sine, I put the 2 in already, times sine of omega t plus pi over 4. J squared is minus 1. To progress, we're going to need to know what the frequency is. Now, we're working at 1 kilohertz, so omega, the angular frequency, will be 2 pi times 1 kilohertz, which is 2000 times pi. And the inductance is 47 millihenries. So all of that together gives me 2 milliamps times 2 times pi times 1000, that's the angular frequency, times the inductance of 47 millihenries, 0.5906. So this is minus 0.5906 times sine of omega t plus pi over 4. That is the contribution of the two current sources. the contribution of the voltage sources, as we've seen before, is just cosine of omega t minus pi over 2. So the next stage is just to add these two up, the contribution of the current source and the contribution of the voltage source. We've got two sinusoidal waves now at the same frequency to add up, and the easiest way to do that is using phasors. First thing to do is we'll have to adjust the way we've written this first term to get it in terms of cosine omega t rather than sine omega t. And we can do that using the useful formula that sine x is equal to cosine of x minus pi over 2, or 90 degrees. So this first term here we could write as minus 0.5906 times cosine of omega t plus pi over 4 minus pi over 2 gives me a net minus pi over 4. Combine that with this term using phasors. Let's consider where the phasors are. The phasor representing this term here is just there at minus j. The phasor representing this term here is going to be at a magnitude of minus 0.5906. Now, what does a negative magnitude mean? Well, the negative magnitude means that it's out in the other direction from this phase. Because cosine of x is minus cosine of 180 degrees, or pi minus x. The angle of this is minus pi over 4, which suggests it's out along this line somewhere down here with an angle of minus pi over 4, or minus 45 degrees. But because the magnitude is minus 0.5906, it actually means we're out the other direction, a distance 0.5906 away from the origin. So that is the phasor representing the contribution of the current source. All we have to do now is add up these two phasors. Well, this angle is going to be 135 degrees, and this magnitude 0.5906. So, if you have a calculator that's good at doing complex numbers, you could type in something like this: 0.5906 at a phase angle of 135 degrees minus j. And the answer is 0.7166 at a phase angle of minus 126 degrees, which is going to be down in this direction somewhere, around about there. That's going to be the phasor representing our answer. So our prediction is that the phasor representing our answer is 0.7166 at a phase angle of minus 126 degrees. So we would expect that the voltmeter would be receiving a signal of 0.7166 volts cosine omega t minus 126 degrees. This calculator works in degrees. So the amplitude received by the voltmeter, we would predict 0.7166. Did we get it right? Let's see what the simulator says. Phew. Yep, we got it right. Now, if you think that was a very time-consuming and difficult process for solving the circuit, you're absolutely right. There are two shortcuts we can make that make that process much, much easier and simpler to do. But they will have to wait until the next few talks.